Hello everyone, you might have heard of Unix philosophy in general and its software design principles in particular, like do one thing and do well, expect the output of every program to become the input to another program, write programs to handle text streams, use shell scripts, and finally, last but not least, avoid captive user interfaces. Now, how this can be applied to actual programming, you might be wondering. So let's write some code that values as many Unix philosophy principles as possible, and then we'll alter it to align with all of the principles listed here. So let's write a very primitive calculator, for instance. So I can say ego and calc.py, so creating a new file. So let's define the expression the user is going to input here, and also provide the variable storing the result. Okay, so say equals to 0. So let's say if we have a plus in our expression, in this case we want the result to be equal to, and just have two integers plus, so converts into integer whatever goes, like expression dot split by this plus symbol and the very first element, and here expression split by, again, plus and the very last element here, and do the same thing for the rest of operations, so subtraction, multiplication, division, and here division, multiplication, subtraction, and here subtraction, multiplication, division, and obviously here as well. So here I can say minus, multiply, and divide. And finally we just want to print the result. Now let's quickly test this, and then we'll walk through the source code in terms of like how in particular does it violate all of the Unix philosophy principles possible. Okay, so just right quit and say python 3 calc.py. So let's say 12 plus 12, 24, good. 43 minus 10, 33, good. Now let's say 2 multiplied by 2, 4. Now let's say 12 divided by 6, 2. It's floating point, but doesn't matter, still so it works. Okay, good. So what you might be wondering is wrong with this particular code. So first, it doesn't do one thing, it does exactly 4 things. So it does the addition, the subtraction, the multiplication, and the division. And on top of these, we can say it even does 2 more things. It takes the user input, which is a separate functionality, and also it outputs the result, which is also can be like separated into a single program, let's say. Now, to make it even worse, we can violate one more principle, so we can actually add the captive user interface here. So if I say simply while true, and this is going to be a loop, and let me just say from the 2nd line to the 7th line, want to substitute starting from the new line and like this, and here let's say print like type in your expression. So another principle that wasn't mentioned in the list is that the program shouldn't output some redundant information to the standard output. So it shouldn't sort of print in some strings that don't quite add pretty much anything to the functionality. So let's run this again. So now you see like 2 plus 2, good, and then type another expression, and so far. So yeah, 40 divided by 10. So now you see like we are trapped in the loop and we're no longer sticking to the standard Unix environment. So at this point, our program has turned into a monolithic beast that lives completely on its own and doesn't care about the environment it runs within. Now, how can we alter this program to actually align with all the possible Unix philosophy principles we know? So in order to do this, we can actually split the functionality and then provide the interfaces, and then make sure we can pipe this single tiny little modules of the program into a single pipeline. Now let's have a look at the source code one more time. First, let's split the tasks this application is making. So we'll make 4 separate programs, one for addition, one for subtraction, one for multiplication, one for division. So simply say, let's call it sum.py. Want to have the expression variable equals to user input, and as an output I just want to print integer plus integer, so converting the string to integer here. Now, to make it a bit more universal, to make sure it will align with other programs, I would not stick to different separators to evaluate the expression. So instead of having like different like plus, minus and so on, we'll use a standardized single delimiter, which is going to be a comma. So here I can say comma, and the very first one, very first like sort of digit in here, expression split, and again comma here, and the very last one like so, right, quit. Now if I say Python 3, for instance, sum.py, all I need to do, I need to say self 12 comma and 13, and it gives me the result of 25. Now let's provide a similar functionality for the rest of the operations we have. So I can simply say I want to copy my sum.py to sub.py, so this would be subtracting. Then I want to create the one for multiplication and the one for division here. So now let's open the subtract one. So here the same, but we only change the sign like this, right, quit. Now multiplication, and we change this sign to multiplication here. And finally division, same, we just change the sign to divide. So let's quickly test this. I say Python 3 sub.py, and let's say 4 comma 2, 4 minus 2 equals to 2, great. Now let's do the multiplication, so 3 multiplied by 9, 27, so far so good. And now let's do the division, so 24 divided by 12 is equal to 2, which is exactly what we need. Now it's not really that convenient to use this Python 3 and so on, so I want to make this tiny little modules to be available system-wide. Now to achieve this, I'll write a simple install script. So say ego install.shell, I want to cp sum.py to user bin, and just call it sum, and here sub, and here mul, and here div, and here div mul and sub. Now I want to make this file executable, so executable install shell and just run it. Okay, now we should have all the commands and the shortcuts like sum 2 2 4, okay, sub 5 3 2, okay, like mul 3 9, okay, and div 18 6. Great. Now let me demonstrate the simplest possible pipeline involving those commands that we've just developed and those already exist within the Linux environment. So for instance, I can say echo and 3 2 and pipe it to the sum, and we have 3 plus 2 equals to 5. Good. And we can use different outputs from different commands and concatenate them together to pipe it to another command, like the one that we just created. So for instance, if I can say paste and specify the delimiter comma, because that's the delimiter we're using, and here I want to say echo 5, this is the output of one command, and also here I'm using echo, let's say 3, and I want to pipe this into the sub command. So 5 minus 3 is going to be equal to 2. Great. So what this means is the following. So we're going to have a bunch of commands resulting in the output 5 and another bunch of commands resulting in the output 3. Now to bring this idea even further, let me write a simple shell script showcasing how this can be done in particular. We'll create a script that would solve a simple expression using those commands that we've just written along with those commands already available in my Linux system. So here I want to use bin bash to execute it, and the expression we're supposed to be solving, so let's say something like x plus y multiplied by z minus let's say y minus x and divided by z, like this. So in order to achieve this, so let's define x equals to, let's say 5, y equals to 6, and let's say z equals to, I don't know, 8 for instance. And let's make sure that this is a script to solve the following expression, and here we have the variables. Okay, now I want to collect the products, so collect products, and let's say product 1 is going to be equal to, so here I'm storing the entire command, so I want to say paste and the delimiter comma, and now I want to echo and the variable x, so we have this x plus y, and the second one echo y, right? And now just to make sure that this sort of works, I want to say echo and prod 1. Now make it executable, and run it. And here as well. Okay, now we have the output, which is 5 and 6, which is good. So the next thing we want to pipe this to the sum command, because that's exactly what we're looking for. And let's run it again. So 11, which is exactly what we need. Now I just want to duplicate this, and this is going to be equal product 2, and this time y and x like this, and this is going to be the command sub. So essentially 6 minus 5 is going to be equal to 1, so prod 2, so it should be equal to 1 now, the result here. Yes, it is. And now let's define the product 3, and equals to, now I want to paste product 1 and here echo and the z variable. So now let's see, this kind of works. Okay, 11 and 8, which is exactly the result we've been looking for, because 6 plus 5 is going to be equal 11. So this is the first argument and this 8 is the second argument. All right, so now we can pipe this to the multiplication here. Okay, and it would now multiply 11 by 8. Okay, 88. So far so good. Now product 4 is going to do the following. So now we're taking the product 2, and first let's see if it's done properly. So 1 and 8. 6 minus 5 is 1 and then 8. Okay, and finally I want to pipe this to the div command. So 1 divided by 8 is 0.125. Good. And I finally want to make the final product 5. Let's call it result actually. So the result is going to be equal to, so we take the product 3 and minus the product 4. Let's have a look at the result. And for now, let's not pipe it anywhere. Okay, 88 and 0.125 exactly, and pipe this finally to subtract. Oh well, okay, that's because those 10 other programs we just developed do not actually support these floating point numbers. So what we can do, let's quickly fix this. So here I want to make it integer like this, and sudo cp div.by user bin div. Okay, and let's try to run the calc again. Yeah, now it does, but yeah, it just does 88. Okay, so there is 0. Okay, so just to make that result not 0 but something else, let's change the value for, so for instance 6 minus 5, let's say edit 18 minus 6. So now yes, okay, let's actually make it 26 minus 10, so that, yeah, so the result of the division is going to be equal to 2. And now finally let's make it like subtract. Yeah, and here we got the eventual result. Now you might be wondering whether this is actually the only way to write the software that aligns with Unix philosophy. Well, obviously not. And just to give an idea what we can do to the source code that we've developed in the very beginning of this video. So there was calc.py. So let's have a look at calc.py. So instead of this monolithic code, we can alter the source code a little bit. So let's go for it. So if I just copy the calc unix.py to calc, call it unix.py, and calc unix.py. So here I can just define a few functions. So whatever single standalone executables we have, we can now use the functions instead. So this is going to be like sum takes x and y and return x plus y. Then can do the rest. So we can do subtract, we can do multiply, and we can do divide, and respectively here plus, minus, multiply, and divide. Okay, and here I can simply do the following. So here I want to say summary, and the first argument as well as the second one, and here I can just say subtract, here I say multiply, and here I say divide. Now let's give it a try. So Python 3 calc unix.py, and here we go. So 2 plus 2, great, 3 minus 1, okay. Now we can actually refactor the code even more. So here I want to define a new function called calculate, and this is going to be taking the operation as the parameter. So I can do the following way. So simply I want to define the dictionary called operations, and this is going to be equal the following. So here let's say plus means that I want the summary, then minus means I want the subtraction, and multiplication, and division. And also I forgot to add the argument 1 and argument 2 here. So eventually this would return operations indexed by operation and specifying the arg1 and arg2. And here to call it properly, so we don't need this anymore. So this is going to be equal like result equals to calculate operation, and this one split by the operation and here. And now if say we do provide the input in a little bit different format, so for instance the format would be like this, so you say like plus and then number 1 and number 2. So in this case we can always rely on the very first element as the operation that we're looking for. So here we can say operation is equal to expression and the first element like this. And also we do not want to split by the operation anymore. So in this case we can split by an empty white space, for instance, and an empty white space like this. So this is going to be the first element, and yeah, this is still going to be the last element. So let's have a look if it actually works. Okay, so plus and 2 and 3, and we got 5. Cool. So minus 5, 4, we got 1. So multiply 3 by 9, we got 27, and divide 18 by 3, we got 6. Now, while Unix philosophy software design principles were not applied literally in this particular program like we did when split the functionality into small microprograms, still the overall idea of modularity and reusability still applies. Now we have function interfaces instead of text-based I/O, and operations lookup dictionary to reference arithmetical modules quite elegantly. Every single function does one thing and does it well, and the Unix philosophy principles are applied within the context of a single application. I hope this would bring some light towards the practical understanding of the Unix philosophy and software design principle. Now, this is it from my side. Thanks for watching and cheers.